Hello, we're going to be talking directing groups today. Now, I have highlighted up some of the different directing groups that we're going to be talking about. We've also got all of these others that we are going to be chatting about at some point throughout the video, but the green and the pink ones have been highlighted up because they're quite important. And we're going to have a look at why. Before we get into the main body of the video, when we're talking about directing groups, I'm going to link back to what you'll have done in previous lessons, and that's about why phenol and benzene have got different reactivities, why we need a catalyst to get benzene to react, and why that's not necessarily the case with phenol. You'll have talked about the electron pair donation from the p orbitals into the pi system from the oxygen. We're going to link that in with 2,4 directing and 3 directing groups. We're going to be linking that knowledge back. I've highlighted up in green and pink here. The 2,4 refers to the OH and NH2, and the 3 directing to the NO2. Really important is this little yellow bit here on the specification, that you will not be expected to know further donating or withdrawing groups, but, and this is the interesting bit, relevant additional data will be supplied. So you'll get a table something like this. You know about 2,4 directing for OH and NH2, or withdrawing for NO2. You're going to then be expected to be able to apply it if you're given some new information. So for example, here we've got the NO2. We know that that's going to be 3 directing, but you'll get given additional information like all of this and be expected to apply it in the same way. So let's get into it. We're going to be talking about 2,4 directing first, groups that activate the ring. And when we talk about activating, oxygen on the phenol has got 2 lone pairs of electrons. We're going to focus in on one of those lone pairs of electrons. So get rid. One of those lone pairs of electrons in the p orbital. Those electrons are donated into the pi system. Now you could also say, rather than it being donated to the pi system, you could say p orbitals donate electrons, or electrons are put into the delocalized ring. And the really important bit here is that that delocalized ring or you could say that pi has become more electron dense. And linking that back to previous lessons, that is why we get a much more reactive compounds. We're going to be talking a bit about it in terms of it being 2,4 directing. You don't need to know why and go into the detail as to why it is 2,4 directing and talking about resonance, and none of that is relevant for you. However, you do need to know how to apply it. So get rid of this. That. Tidy up my diagram. So we're talking about 2,4 directing. Now, when we're doing 2,4 directing, we need to number it up so we know what we're talking about. So we've got 1, 2 carbons, 3, 4, 5, 6, or number 1, number 2, number 3, number 4, number 5, and number 6. So when we're talking about 2,4 directing, and let's use chlorine for an example. Cl2, we're going to substitute in chlorine, halogenation. It could be substituted in on the 2,4. So let's focus on 2 for the moment. 2 location or 2 location. It could also be substituted in on, let's use green, location 4. Now in this situation, we have got in black Cl substituted on in this situation, we've got Cl substituted on the 2 location and on the 4 location, which we can also say is location 2. And then we've also got the chlorine substituted on position 4. Now looking at that in a little bit more detail, we've got 3 locations, 2 of which are equivalent. So we've got 2 out of 3 are in the same place. So about 67% of the time, we're going to get substitution on the second directing group. That leaves us with 1/3 are in position 4, about 33% are being directed to the 4th location. Let's have a look at this in terms of the amine. So amine NHH. The nitrogen's got a lone pair of electrons. That lone pair of electrons we can then focus in on thinking about its p orbitals, which donate electrons into the pi system, increasing the reactivity of it, and in doing so, directing any substitution to the 1st, 2nd, 3rd, 4th, 5th, and 6th. Again, looking at position 2, could substitute a chlorine there, or position 2, substitute a chlorine there. I realise I've done that in completely the wrong colours. Let's redo that. We could substitute into position 2 here, or we could substitute into position 2 here. There, that's much better, isn't it? Colours actually match the colours. Or we could substitute onto position 4. For the exam, really importantly, they're only going to be talking about mono substitution unless they state specifically that they want other substitutions. So if they want 3 substitutions taking place, then you're looking at 1, 2, 3 substitutions. But the standard is they're only going to want you to substitute on once, so a mono substitution, in which case you're then looking at something like that, a mono substitution. Let's have a look at 3 directing and then have a little bit more of a chat about what's going on, and then we can start having a look at some examples. So 3 directing, groups that deactivate. You remember which one is specific to this course? Yep, you got it right. NO2. Now, again, we don't need to know why NO2 is a 3 directing, why it's specifically in the 3rd location. 1, 2, 3, 4. So why does it direct onto there? We don't need to go into that in any detail. We just need to know that it does and be able to apply that. If you want to know, talk about why it is a withdrawing or a deactivating group, because you've got nitrogen bonded onto an oxygen, bonded onto an oxygen. Nitrogen, yes, you've got a lone pair of electrons, but Oxygen is very electronegative. It's pulling electrons away from the nitrogen, and therefore it's not going to be able to donate with the same ease those electrons in the lone pair into the pi system or the delocalized ring. And in fact, we'll pull electrons out of the ring, making it less electron dense and therefore less reactive. So, 3 directing groups, a bit like in the 2-4, we can count clockwise or we can go anti-clockwise. 1, 2, 3, 4, 5, 6. So if we're talking 3 directing, we can talk directing there or directing here. And that time I did get the colors right. Yay. And that's it. When you're looking at application, first and foremost, look at it. Is it talking about 3 directing or are we talking 2 directing? Have a look at what is bonded onto the ring. So you might get, for example, let's get rid of these. So it said you might get, for example, a compound that is referred to and they'd ask you what the monosubstituted product of this compound might be. Let's highlight it up. We've got COOH group. Therefore, we are looking at this. Therefore, we're looking at 3 directing. Let's number it up. 1, 2, 3, 4, 5, 6. Directed as 1, 2, 3, 4, 5, 6. That means that we're going to be looking at either a substitution happening here, substitution happening here, but because they are the same position, if we just flip the molecule around, flip it over, we can say that those are equivalent environments. And therefore, we're looking at monosubstitution. You can draw it like that, or we can draw it like that. Finally, let's have a look at some worked examples. This might look familiar to you guys. It came out with the lesson. We had a couple of questions about it. Part of this is going to be analysing the question, pulling apart what the question is asking us and picking out key bits of information. So, highlighter. How do you form 3-bromo-nitrobenzene? 3-bromo-nitrobenzene. Well, first things first, I would be looking to do is draw out the molecule, because then that gives me an idea of what I'm working with. 3-bromo-nitrobenzene. So we're going to draw on the NO2 group first. Actually, that's really messy. Let's just get rid of that. NO2. And 3-bromo. Because we've got first carbon, second carbon, third carbon. What do we know about NO2? We know that it's 3 directing. Going back to some of the previous tables, we know that any of the halogens are 2,4 directing. So we could either go route 1, We first nitrate, we could look at route 1. First, we add NO2. Second, we add the Br. Or second option is first we add Br, then secondly we add the NO2. We've got to make a decision for this one, which one would work. Let's add a bit more annotation onto this. This is 3 directing, and this is 2 4 directing. This is 2 4 directing, and this is 3 directing. So if we add in the NO2 first, then that means that anything else we add in subsequently, anything else we try to substitute in, is going to be directed to 3. If we were to substitute in Br first, then any subsequent substitutions would go to the 2nd or the 4th location. Going back to this compound. 3-bromo-nitrobenzene. 3. Bromine is on the 3rd carbon. So we must first nitrate, then we can brominate. Down here, 4-bromo-nitrobenzene. Firstly, we're looking at 4-bromo. So paste, shrink that down a bit. NO2, 4-bromo. So 4-bromo, we're on the 4th carbon. We know that bromine, because it's a halogen, that's a really scruffy arrow, apologies. Bromine, because it is 2 4 directing, if we substituted the bromine in first, then when we tried to nitrate, the NO2 would appear on the, not the 1st, possibly the 2nd, 3rd, and then the 4th. So if we wanted to form 4-nitrobenzene, we would need to substitute the bromine in first, which would then cause the NO2 to be substituted onto the 4th or the 2nd. And in this case, we've been asked to do 4-bromo. So let's have a look at some examples. Chemist carries out an investigation into the reactions of substituted benzene compounds. Table below shows the stated effects. So we've got a table, we've been told a little bit of information. It looks a bit different to the table that we're used to, but it's the same idea. It may look different, it doesn't matter, because we've got the groups here, and then we've been told, hold on, NO2 we know about is 3 directing. OH is 2,4. And then we've got a whole load of ones that we don't know about, or we're not expected to learn, but that's because we're being told where they direct to. And we can then just apply that information. So we're being asked about the mono substitution. So first and foremost, we're looking at the CN. CN is 3 directing. So let's put our benzene ring in. N, we know it's 3 directing, so let's count around. 1, 2, 3, 4, 5, 6. Mono substituted, we're only going to be adding in 1 chlorine, so we're going to focus in on this location, Cl. Now, if you're not happy with that and you think, oh, that looks a bit scruffy with the numbers on, you can always rewrite it out, paste. There we go. Now, let's have a look at the second example. Mono substituted. Again, we need to be careful we don't get carried away. Talk about mono substituted. Let's have a look at the functional group that is added onto the benzene ring. So we've got this group. Let's identify it up in the table, and it's 2, 4. So again, let's come down, put our benzene ring in, paste. So we've got first carbon, second carbon, third, fourth, fifth, and sixth. Or first, second, third, fourth, fifth, and sixth. I'm feeling lazy, so I'm just going to copy this out so I don't have to keep on drawing it. Now, there's 3 marks available here, product or products. I'm going to just highlight up the products because that's going to be quite important. So we know that the NHCOCH3, that directs to the second or the fourth position. Notice, because of its increased reactivity, because it is a donating and activating group, Cl2 doesn't need a catalyst to react with the benzene ring. So we could substitute on to the second, which is exactly the same as saying onto this side, but we're talking mono substitution, so we're not going to double it down. Or the fourth. And that is why we're looking at 3 marks here, because we have got only 1 product formed in the first reaction, but there are 2 potential products in the second. So that's 1 mark, 2 marks, 3 marks. The reactions C6H5N CH3 brackets 2 are similar to that of phenol. Draw the organic product that is formed for the tri-substitute. Now I'm going to highlight up tri-substitution with chlorine. First things first, let's draw out our molecule. Just FYI, this is something that really bugs me. I've drawn it like this. The amount of times people draw carbon, CH3, drawing that CH3 bonded via the carbon, and they will lose marks in the exam as a result. Very, very frustrating. Make sure that you draw it, the carbon bonded to the nitrogen, nitrogen bonded to the carbon. Don't write it the other way around, so it's CH3 then to the nitrogen, because you'll drop marks. And we've been told that that looks like phenol. And what do we know about phenol? We know that phenol is a 2,4 directing group. Because it's 2,4 directing group, so we're looking at directing onto here or here. So we're going to get substitution there or here. Now we're talking about a tri-substitution. So we already know that it reacts the same as phenol. Phenol is 2,4, and we're looking at 3 substitutions taking place. So let's shift this into the center. So we're going to get substitution onto 1, 2, 3 different locations because these are both considered 2, 2, and 4. So let's substitute on Cl, Cl, Cl. Okay, and that is our 1 mark, nice and easy. Explain why chlorine reacts more readily with this compound than it does with benzene. Now, that's the interesting bit. We know it's 2,4, 2, 4 directing, which means that it's an activating group. When we talk about activating, there's a couple of things we need to mention. Lone pair, p orbital, pi system. How many marks are we looking at here? 3. So we're going to want to make 3 nice clear points. Point number 1. We've got the nitrogen has a lone pair in a p orbital. 2. We want to what's happening with that lone pair in the p orbital. You can say it merges with, or donates, or pushes 2 electrons into the pi system. You could also say delocalized ring. And as a result of that, you've got a greater electron density. And so more able to induce the Cl2 molecule. And then it's going to be more reactive, it's going to be more able to react with, it induces a dipole, pulls out a pair of electrons to bond to the chlorine, breaks the chlorine bond, and you get substitution taking place. I hope that all helped. I hope you found that useful, and I look forward to talking to you guys soon. Bye.